Okay, just a little while ago we were talking about me punching Tyler in the face, and why not? Now we're going to analyze the graph. We had two punches, one of which in green, where I just moved my fist at a pretty constant 5 inches per second for 6 seconds, covering 30 inches of distance, and a second punch where I did nothing, represented by the blue. That's this part of the piecewise function. We decided that this parabola described my effort to accelerate my punch across Tyler's face, and then my fist did nothing but sit there for the remaining 1.9 seconds. Now, we were talking about this in the context of the difference between average and instantaneous rate of change. Average rate of change over the whole 6-second interval is the same. For the first punch, I just moved my fist 30 inches in 6 seconds. The second punch, I did a whole lot of other things, but if you look at the entire 6 inches, the result was the same. If you look at this whole 6-second interval, my fist still wound up 30 inches from where it started. So, the average rate of change, I would have to say, over all 6 seconds was the same, whether you're doing this, or whether you wait 4 seconds and really haul off and hit somebody. But do you think Tyler's chin would have felt a difference between the two punches? Between me slowly moving my fist across the space and me waiting and going as fast as I can.
Yeah, some areas are more sensitive than others.
Well, aside from, not even talking about what point of contact, but I'm just thinking about how fast the impact would be. So, I guess the question I'm sort of leading up to here is, this 6-second interval is fine for looking at my fist going like this. Is this entire 6-second interval a smart idea if I'm looking for how fast my fist was moving right at that instant of contact with Tyler's face? Should I be looking at this whole 6-second interval to find out what happened here? No, I need to start narrowing this down.
It's only like a little over 1 second interval. I mean, if you're going from 3 to like, if you just want to like...
Let's start shrinking it down. Okay. Let's go with integers. So, for the second punch and the first punch, okay, the average rate from t 0 to 6 was 5 inches per second, right?
Mm-hmm.
Average rate for both punches over 6 seconds, is 5 inches per second. But that's sort of an insane interval to look at if you're really only interested in what happened here, right at the point of contact. Okay, so let's narrow that down a little bit. Let's start with integers. What was on just the second punch, this is all we'll talk about now, what was the average rate from t, let's just say, how about 4 to 5, because that's the 2 integer seconds between which the punch took place. Does that make sense as a place to start narrowing our range?
Yeah. Okay.
So the average rate is going to be, average rate, we said we could look at that as f of x plus delta x minus f of x over delta x. Alright, well, this is fairly simple. F of x plus delta x is the y value when we're done. When I'm done with at 5 seconds, my fist has moved 30 inches, right?
Mm-hmm.
So, that's my final y value. Where did my fist start? 0 inches. How long a time interval are we now talking about? 1 second. Okay, so we've now taken our average rate of change of 5 inches per second over the entire 6-second interval.
Wait, 1 second? Wait, is it x distance?
Not anymore. What's my x-axis representing here, I mean?
Time.
Wait, oh.
Time.
Okay.
I think you're in
Y
physics mode.
distance
Yeah,
X is
time.
time.
Okay, so that's 1 second. In general, you're right. Welcome back to pre-calculus. So this is just going to be 30 inches per second. Okay, so that seems a little more believable for that second punch, the faster one. There's no way I really hit him at 5 inches per second on that one. But keep in mind, if I looked at from 4 to 5 on the first punch where my hand was moving steadily, here my average rate of change would still be 5 inches per second. The slope of that secant line is not changing. But if I look at from 4 to 5, here's where I'm getting a much steeper slope. So that's a little more believable. But do you think that's enough to really describe what's going on here at 4.1 seconds? Right at that moment of contact? I mean, I know the punch was only the first 1/10 of a second, right? So for that remaining 9/10 of a second that we're still talking about here, I was done. So do you think maybe we should shrink that interval a little bit more?
Yeah.
I think so too. I'm going to take a moment and redraw this, okay? I want to see what we're really talking about.
You what? You just erasing it?
Yeah, I'm going to draw it again.
But I missed what you drew from the
Oh, it was the same as it was up there before.
What?
It was the same graph. I didn't redraw that. That was the same graph.
But
that
did
was
you
up
draw
there.
in something new?
No.
Okay.
No, I didn't.
It just looked that way from... Alright.
You're good. And I have a picture I took if
Alright. I mean, I have it. I have the other one written down.
Gotcha. Okay. Alright, so for the second punch, I'm going to break up my graph a little bit. Put this little mark in to indicate I'm skipping some time. And I'm just going to look at from 4 to 4.1 seconds. And this is still going to go from 0 to 30 inches. And now, on this very skewed graph, we have, I said this would be the vertex of a parabola as I was trying to accelerate. Remember that parabola there that I stretched out, that was just that really narrow little red parabola that you didn't even look like a parabola on the first one. Okay? So, let's see if this starts to make more sense. Now what I've graphed is this parabola, y equals 3,000 x minus 4 squared, which we're saying represents my effort to throw a fast accelerating punch. We're going to forget about this average rate of change of 5 inches per second. And you know what? We're going to forget about this average rate of change of 30 inches per second, but I'll leave it up here for a second. You know what interval I think makes more sense?
What?
I think we should just look at while my fist was moving. Why would we care about when I was sitting still or after I'd thrown the punch? Let's take a look at the slope of the secant line that cuts across this graph over that 1/10 of a second. So the slope of that line is going to be, once again I wound up at 30 inches. I started at 0 inches, those are my y values. My x values are time. I was finished at 4.1 seconds. I started at 4.0 seconds. So I'm getting 30 divided by 0.1, which will equal 300 inches per second. Okay, so let's think about what's going on here. I start with looking at all 6 seconds, and I seem to only have an average of 5 inches per second. I look at the 1 second in which I threw the punch. I have an average of 30 inches per second. Now I look at just a 1/10 of a second during which I was actually throwing that second punch, and I have an average rate of 300 inches per second. Now, I was saying a minute ago that we were looking for an instantaneous rate of change. And I said last period that you could think of the instantaneous rate of change as not being a slope between 2 points, but a slope that touches at a single point. a tangent line instead of a secant line. Now, looking at this, I need a slope that describes what the curve is doing. Does this secant line look like it's really describing what's going on right at this instant of contact? Does this look steep enough? Danny's shaking his head. How do you feel about that, Remy?
Looks good.
You like the secant line? But see, I don't like it. I'm thinking of a tangent line. I need one that describes what's going on up here. I'm thinking...
You need to draw like another line that's vertical from the...
Well, more steep, I would say, not necessarily
Yeah,
vertical.
maybe not, yeah, but I mean like it's more... I think you know what I mean.
Okay, well, I'd like to think in
Like-
terms, not so much as just drawing it. You're thinking geometrically, which is good.
Yeah.
Visual. Here's what I want to do. I want to shrink this time interval more.
Oh, okay.
Will that get me that effect? Like, here's 4 to 4.1 seconds.
You can make it like 4.05.
I'm going to go even further. I'll make it 4.09.
Okay, that's really close.
Because, let's think about this a sec. Really, my whole premise is that I didn't come in contact until 4.1 seconds, right?
Mm-hmm.
So, I need to know what's going on as close as possible. So now what I'm going to do is I'm going to look at a secant line, another secant line. The red secant line represents this whole 1/10 of a second while I was throwing the punch. This green secant line
Wait, what's
represents...
the weird thing?
Pardon?
Why does it go like up and I'm like...
Oh, I was just trying to line up well. This part, I'm sorry, is not part of the secant line. I shouldn't leave that in. The secant line is just from here to here. From this point, 4.09, comma something, up to 4.130. Okay, here's where I need somebody to pull out a calculator and find out what happens when I put 4.09 in for x. Or I can see if I can do it without one, but I need to know that value.
For x at 4.09?
Yeah. So I'm looking for y equals 4.09
Oh, wait, no, you're looking for...
minus 4 squared. What's y going to be? Whoops, I left out the 3,000, didn't I?
Yes you did.
Okay, so that's 3,000 times that.
24.3.
24.3. Awesome. So here we're looking at a slope of, let's see, we started at 30, we ended at 30, we started at 24.3, we ended at 4.1, we started at 4.09, so I'm getting 5.7 divided by 0.01, so now I'm getting 570 inches per second when I shrink that interval even more. We started with 5 inches per second as an average speed for my fist. Then we got 30 inches per second as an average speed when we looked at 1 second of time. Then we looked at 1/10 of a second and we got 300 inches per second. Then we looked at 100th of a second, and it seems like at this point my fist had accelerated to a speed of 570 inches per second. That's not good enough for me. I want to know what's happening even closer. So you know what I'm going to check next? I want to know what's going on at 4.099 seconds. I'm not sure I can even draw this in a meaningful way. So let's see, that was the green one. This we said was 24.3. So this is going to be 4.099, comma. Remy, put 4.099 into my parabola. What is my y value? What's the slope of this secant line? 30 minus something. 4.1 minus 4.0.
29.4.
29.4. Can you go out a few more decimals for that?
03.
03? Okay. 29.403. So this is going to get me 0.597 over 0.001, or 597 inches per second. That's the slope was that? 0.4, 29.403. Okay. Now remember, this slope represents a rate of change. We're talking the change in position of my fist. So if we look at the whole 6 seconds, my fist was only moving at 5 inches per second. If we look at just 1 second, my fist was moving at 30 inches per second. We look at a tenth of a second, the whole time my fist was in motion, I seem to average 300 inches per second. We narrow that down to a hundredth of a second, 570 inches per second. We narrow that down to a thousandth of a second, and it seems like my fist's average speed for that thousandth of a second is 597 inches per second. What's happening here? As we look at smaller and smaller intervals, closer and closer to that
It gets
point.
higher, it goes faster, and, well, not fast, the velocity, now I'm talking physics.
Alright, well go ahead, talk physics.
The velocity, sorry people who don't know physics, the velocity is going to get higher because it's going to be less, or like you're going to be going a greater different distance.
Well, we're talking about instantaneous. This is where it gets confusing. Because, I mean...
I don't know, I'm thinking too much like a physics
You are thinking too much like a physics problem. Because we're not really talking about going a greater distance. I mean, we actually look like we're talking less and less distance. But we're doing that less and less distance in even shorter and shorter time intervals. Yeah, so that's where velocity comes in.
If you get into decimals, it actually makes the final number bigger.
Yes.
So it's weird.
Yeah, you get the decimals in the denominator, making the numerator get bigger. Check out how the averages are changing though. We went down to a tenth of a second, and this jumped to 300 inches per second. Then we went down to a hundredth of a second, and this went up to 570. But then we went to a thousandth of a second, and this only went to 597. I mean, it got 10 times bigger, almost twice as big, and then just a little bit bigger. So we're going to do this once more, and I'm not even going to try and graph it. But I want to know what happens. What would the slope of a secant line that cuts across this parabola just between the time values of, that was supposed to be 4.1 there, sorry. Did I make a little mistake? Remy, you're supposed to catch things like that.
What? Sorry.
This middle one, that was this 4.1. We're starting with y sub 2 and x sub 2, so it should be where we ended, which is 30 and 4.1.
Which one are we doing now?
Well, now we're going to go out to 4.0999. We're going out to 1/10,000 of a second. I'm not even going to try and graph it. I'm not going to try and zoom in that close on my drawing. But what I would like for me to do is plug 4.0999 into the calculator and give me out to a fair number of decimal places what the y value is on that parabola representing where my fist is when I throw this punch.
29.94003.
29.94003?
Yep.
Okay, awesome. So what we're getting now is 30 minus this is going to be 0.05997 over 0.0001. And so this is 599.7 inches per second. Okay, so we can keep narrowing the time interval and look what happens. We jump from 5 inches per second to 30 inches per second. Every time we narrow that time interval by a tenth, we go to 300 inches per second at a tenth of a second. We go to 570 inches per second when we look at just that last hundredth of a second before impact. We look at that last thousandths of a second before my fist would have hit Tyler's jaw, and we only jump from 570 to 597 inches per second. We go down to 1/10,000th of an inch of a second.
It's like with the bank account with the interest rate.
With the interest rates, when we prove that you can't get more than $2.72.
And it's like with the limit of infinity, it's just going to get little, it's like it's going to get
like an
smaller and smaller and smaller.
You asked like an hour and a half ago, is this like an asymptote?
Yeah,
and I said sort of.
Kind of.
How fast do you think my fist actually hit Tyler's face, according to this model?
Not very fast.
Well, this is still pretty quick, but I mean, not how much faster than this, but...
Not that.
What do you think I'm going to keep getting closer to if if we keep going to like another time interval down.
You're gonna keep. I mean, you're gonna hit 600, obviously.
Looks like we're heading towards 600, right? So if I had to guess from this, I would guess, and it would be a guess from this, that my
Pretty damn accurate.
it's a good guess, that my instantaneous rate was, and I'm going to put an approximately here because I don't know for sure. I'm saying I hit them around 600 inches per second. So I don't think looking at the whole 6 seconds of time on that second punch was very useful. I don't think looking at the entire second in which the punch was contained was very useful. 1/10 of a second, or at least in the right order of magnitude. 100th of a second were close. 1,000th of a second, honestly, were close enough. And if we keep going, you're right, we will find out that it really looks like my fist would have hit his jaw at 600 inches per second. Is that a little bit different than that first punch, which would have hit it 5 inches per second?
Yeah, very different.
So if you're talking about any sort of impact, which is more useful? The average rate of change or the instantaneous rate of change?
Well, actually, wait.
Which one do you really want to know
I
about?
really want to know the instantaneous.
Yeah, you really want to know the instantaneous
I mean,
rate of change.
unless you're swinging, your entire swing's like that.
Right.
Unless you're moving at like
Unless something's hitting you at a constant, unless something's moving at a constant velocity.
when it hits you.
But then we're back at that 8th grade problem of the car that goes, 50 miles an hour for 6 hours and does nothing to change it. How often does that really happen?
Not very often, but I mean, if someone's punching you, and like they just like from like the first second they get up the speed and just keep that speed.
You're right. An
then
average
it's
speed
gonna
would be
stay.
useful. Right.
So I mean, in
That's a pretty
situations like
horrible
this
boxer.
one,
Yeah.
it's, I mean, like that's could happen. Like that's not gonna, like with a car, no. Like,
You're not wrong. You're not wrong. But you're always really, in any sort of impact, I'm really curious what's happening in that instant. This would be a very tedious way to figure out instantaneous rates of change.
mhm.
I'm going to show you another slightly less tedious way before we get to the real non-tedious way to do it. You guys ready?
I guess.
All right, like you have a choice. Take a deep cleansing breath. We're now going to ask the same question in a very, very different way. So we're going to do this with the notation that I started off talking about. You ready?
Alright.
Okay. I'm going to actually take a picture of this before I erase it.
What, did you say we're going to do slightly less tedious and then a very less tedious one?
Yes. Exactly right. So this will be slightly less tedious than what we just did. And we'll see what happens from there. Okay. Now, okay. I gave you a different notation for slope. Remember, the original question was, how do you find an instantaneous rate of change? How do you find a slope at a single point? And the problem was 0/0 showed up. That was the problem with the slope. We were asking ourselves this question, whether we were really thinking it through or not. We were saying, what is the slope between 4.1 comma 30 and 4.1 comma 30, which is the same point. That's what we were asking ourselves when we're trying to find out how fast we actually hit Tyler. And the reason why we had to go through that tedious process is because if we just look at the slope between a point and itself, we get 30 minus 30 over 4.1 minus 4.1, or 0/0. Yeah. So, we can't do that. Can't. Cannot exist, cannot be the answer. Indeterminate form. We talked about that at length before. But remember, I just wrote slope a different way. I wrote slope a moment ago as f of x plus delta x minus f of x over delta x, and I said what we were really asking for was the limit as this x interval approaches 0. Remember, this is a different sort of limit. Limits we talked about before were when x moves left and right. Now we're talking about when an interval shrinks. I'm going to ask you guys to make a jump of imagination. This is what we were just doing. Remy, like you asked about a minute ago, the delta x, the difference between two x points represented a change in time on that axis on the graph I just had up, correct?
Yeah.
Okay. First, we looked at 6 seconds. Then we looked at 1 second of time. Then we looked at 1/10 of a second, 100th of a second, 1,000th of a second, 1/10,000th of a second. Was this delta x, this time interval, approaching 0?
Sorry?
On that graph I just had, delta x was a time interval, right?
Yeah.
So as the time went from 6 seconds to 1 second, to 1/10 of a second, 100th of a second, 1,000th of a second.
Yeah, it was decreasing.
It was decreasing, so the limit, as our time interval got closer to 0, and this was always 30, and you were telling me what this was each time, as we got closer. We were doing this. Let's fill in some things. My function that described the punch, I said, was 3,000 x minus 4 squared, correct? Is that what I
yes.
said? Okay.
I believe it is.
I believe it is too. So what would f of x plus delta x be on this same function? What do you do with whatever's in the parentheses?
You add them. They replace the.
They replace the x. I love how you said that. They replace whatever's here replaces the x. So I'm just going to take this x, and I'm going to put an x plus delta x in. So it seems like what we were actually doing was we were finding the limit as delta x approaches 0 of the bottom we have our delta x. On the top we have 3,000 x plus delta x minus 4 squared minus 3,000 x minus 4 squared. Take a moment, double check me, make sure I have put in my y values correctly, substituted correctly, and please remember this is still just a slope. This is still some y minus some other y over some x minus some other x. We're just asking what happens when these x's get really, 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 really close together. That's what we were doing. We were taking our two time intervals on the x-axis, making them shrink from 6 seconds all the way down to 1/10,000th of a second. I'm going to leave this on the board and work on the other board for a second now, for a few minutes now. Okay. Any questions on what I did on that board? Setting up my slope. Okay. Now we're going to solve this limit. Solving a limit is just deciding when to let a dog off of a leash, like I said. Because right now, if I let delta x approach 0, this will go away. This term will then be identical to this term, and that will be a 0 on the bottom. I'll have 0 over 0. That's not allowed. Can't happen. Indeterminate forms, there's always got to be a way to work around them. Okay? So I have to solve this algebraically. I will give you your
So
first...
wait, that came from that red and blue equation, right?
Yep.
And then this,
I'm just
Isn't
transferring, yeah, I'm transferring the slope I did over here, the slope equation I came up with, over here. And again, my real goal is to get you guys hopefully to see that this is exactly what we were just doing with plugging in those numbers on the punch. We were taking the y value when we were done, which was 30 inches, minus the different y values that Remy was giving me, the 29.4, the 29.403, and putting them over shrinking x intervals. We're just now going to do it in general, in the abstract, instead of with specific numbers. Okay, remember what I said about sigmas being a semi-permeable membrane the other day? Certain things can pass through them? Okay, I have a 3,000 in both terms in the denominator. I can factor that out. And I can even write it on the other side of this limit expression, because this limit is like a semi-permeable membrane. Some things can pass through it, can be written, some factors, not terms, factors, can be written on either side of it, and it doesn't matter. What tells you whether it can pass it or not is if a delta x is involved. Whatever the limit is talking about, this is the limit as delta x approaches 0. That means nothing with a delta x in it can jump from this side to this side. But 3,000, that's just a number. That doesn't have a delta x in it, so we can write that on the outside. That rule will come in handy later. And now I'm left with a slightly more reasonable looking numerator that I have there. Now here's the annoying part. There is no way around expanding this trinomial. We just have to multiply that out. Okay? I'm going to do that separately. I'm not writing an equal sign. Okay? Now, I'm going to distribute each term from the first trinomial to each term for the second. This gives me x squared, right, plus delta x times x. Okay, so I'm going x times each of these, minus 4x. I've distributed the x to all three. Did I do so correctly? X to here, x to here, x to here.
Yes.
Hope so. Now I'm going to distribute the delta x to all three. And I'm going to put my terms into columns. So I'm going to get another delta x times x. Then I'm going to get, I'll put this out here, because I don't have a term for column for that, delta x squared, delta x times delta x. I don't have just a delta x by itself column, so I'm going to put minus 4 times delta x. How am I doing with the somewhat ugly algebra 1?
Remy, how's he doing?
You're the one who usually catches my details, Remy. Delta x times x,
Yeah.
delta x squared, minus 4 times delta x.
Yeah, that's right.
Excellent. Now I've got a minus 4x. Okay, I've got a column for that. Now I've got a minus 4 delta x. Okay, I have a column for that over here. And now I have a minus 4 times minus 4 plus 16. Okay, so my end result, let's go back to a black for it, is, after I
Oh, I see.
expand
You're
on it,
setting this up like a huge, long addition.
it does look kind of like that.
subtraction.
Just putting the place values, not the, well, same thing really, the like terms together. So I'm going to get x squared plus 2 delta x times x minus 8x, I hope, yeah, plus delta x squared. Why does something suddenly bother me about that? No, no, okay. Got it, okay. Minus 8 times delta x plus 16. How'd I do? Got
I'm
good?
just gonna assume you did it right. I am not.
I'll give you guys a,
Yeah, I think that's right.
I think so too, but thank you, Remy. This is okay, this is gonna get uglier for one more step, and then it's going to get much less ugly. Okay, there's light at the end of the tunnel. And this
I guess I'm
is...
going to heaven then. Oh, your math is killing me.
Apparently so. Wow, that was a good, that almost sounded like you segued into a blues song there, Danny. Okay, I'm gonna stop there and go back to this board. I'll copy it over real quick. And don't worry if this isn't clear yet. This is the most confusing conceptual leap in calculus, and we'll refer to it often, and you don't, I'll be brutally honest, you don't actually have to understand this in depth to be successful with the problems in calculus, with all of them, but it definitely helps on some.
That's not the final answer, is it?
Oh no, no.
That's right.
This is going to get worse for one more step,
That's right.
and then it's going to start getting better. Okay, so the limit,
No pain, no gain.
there you go, I like that. So we'll go back to the limit as delta x approaches 0, whoops. What we're talking about is the slope of a tangent line on this parabola. So I've got to write the 3,000. I have to write the limit as delta x approaches 0. I need a long fraction bar for this. Now on the top, I've expanded the first one, and I'm going to have x squared plus 2 delta x times x minus 8x plus delta x squared minus 8 delta x plus 16 minus, I'm going to expand now my x minus 4 squared. This should seem easy now. That's just going to be x squared minus 8x plus 16 all over delta x. Now, a limit is like a dog on a leash. The key to success is when do you let this dog off the leash? Well, right here, if I let delta x equal 0, that will go away, that will go away, that will go away, and I'll still have x squared minus 8x plus 8x, 16 minus 16. I'll still have 0 over 0. So we cannot yet let the dog off the leash. But we're getting closer. And I just gave a big hint into part of it. So guys, what's x squared minus x squared?
Nothing.
Nothing. Get rid of them both. What is negative 8x minus negative 8x?
Nothing.
Nothing. Turns into addition.
Wait a minute, you're missing.
Oh no.
Did I leave a
No,
turn on
no,
top?
I might be missing. No, never mind, never mind.
Thought I counted 1, 2, 3.
Yeah, I was in parentheses. I thought I was missing.
Gotcha.
something there.
Okay. And now, what's 16 minus 16?
Sorry to scare you.
Nothing.
Nothing. Those all go away. All right, this is starting to look better. The entire second term just disappeared. And we're getting 3,000 times the limit as delta x approaches 0 of, now my numerator is 2 delta x times x plus delta x squared minus 8 times delta x over delta x, and that's all that's left. Suddenly this is starting to look almost reasonable.
Almost.
Almost.
They're funny manners.
But I still have my problem. I cannot let this dog off the leash yet. Because if I let delta x reach 0, if I let this limit just happen like a clean substitution, like just put in 0 where I see delta x, I'm still going to get 0 plus 0 minus 0 over 0. And that's a problem. Is anyone starting to see a hint as to a way out of this?
Oh, take out the beta x.
Delta.
Yeah. Yeah.
delta x.
Take out the delta x's where?
Out of the top of the numerator. And so it's
You guys
delta
are good.
x
What's going to be left?
parentheses 2x plus delta x
Uh-huh.
minus 8
Awesome.
over delta x.
Over
And
delta
that will
x.
cancel out, so you just get 2x plus delta x minus 8.
Those will cancel out.
Is this like one of the, oh wait, it's not squared. It's,
No, okay. Now wait, these delta x's are gone from the top and bottom. What's going to happen if I let this dog off the leash now? I'm going to let delta x be 0. Make it treat it like a substitution
and
instead.
then you're going to get 2x minus 8.
Boom!
And you get x equals negative 4.
Bring the 3,000 over. Hang on, don't worry about that yet.
Oh, screw it, I forgot about that.
Alright, and 2x minus 8. The limit's gone because we let delta x equal 0. We performed the operation of the limit. We let it reach its limit. Suddenly we actually care this much about where the limit is headed. And we didn't have any limits or anything confusing left. What you guys have just done is found something called the derivative function. And here's what you guys just discovered. You discovered that if the function is 3,000 times x minus 4 squared, then the derivative, f prime of x, indicated with an apostrophe here, is 3,000 times 2x minus 8. Now this is called the derivative function. What the derivative function does is it is a formula. And this function tells you the slopes of tangent lines at any point along the original function. And that was our original goal, remember? This whole point was, this was a y value minus a y value over a change in x. As the change in x shrunk so much that we could stop talking about a secant line between 2 points on a curve and start talking about a tangent line at 1 point along the curve. That we could stop talking about average rate of change and start talking about what happens at an instant, an instantaneous rate of change. When x equaled 4.1...
Was that f of 1?
Nope, that's f prime. That's an apostrophe. It's called f prime. What we just did is found the derivative, and this is called the derivative function. This is about the most important concept in calculus, and it gets easier. Okay? Our original question was, how fast was my fist moving when I hit Tyler? We decided this parabola modeled pretty well my fist accelerating past Tyler's face. And we were wondering what happened at 4.1. Well, we know that f of 4.1 equaled 30 inches. That's how far I'd gone at 4.1 seconds, right? Now take a look at this. F prime of 4.1. Plug 4.1 into this. What do we get?
Probably not the same thing, I'm sure.
Oh, ye of little faith. 3,000 times 2 times 4.1 minus 8. 2 times 4.1.
Oh.
What's your guess?
I want to guess it's the negative?
No, hang on.
Not the negative, sorry. I mean, it's the...
Okay, don't guess there yet. Figure it out. Okay, so 2 times 4.1 is 8.2, right?
Yeah.
Take away 8, you get 0.2. 0.2 times 3,000 is?
Is 600.
Yep. So the derivative formula tells me exactly. This proves, remember we guessed a few minutes ago that we said it looks like we're getting closer to 600. You said that, Danny, like an asymptote?
Yeah.
The derivative tells you what happens when you hit the end of the asymptote.
Wow.
The derivative actually says you're no longer talking about getting closer and closer and closer. We can't ever found it. We just found it. Because we set it up in terms of slope with that x plus delta x way of expressing slope. We took the limit as that interval, this delta x got closer and closer. We found an algebraic way to get rid of all the delta x's except one so that we could find a formula that would go from telling us the slope at a secant between 2 points to the slope at a tangent, the slope at 1 point. And we proved that if my original parabola here is a good model of my punch, if this works as a model of my punch, then our guess was a really good one because my fist would have hit Tyler at exactly 600 inches per second.
You
Yes,
just-
Okay, great place to stop. All right, this is the derivative function. And we'll talk about homework real quick right now.